Well, good morning. This is unfortunately 8:37. I had been here about 10 minutes early. I was working on getting rolls off the sheets of paper into a roll book because I thought maybe we were through adding students now. I was busily doing that and then noticed it was 8:33 and nobody was in here except me. So I went down to the restroom one last time, came back, and still nobody here, so we'll go on and get started. This is supposed to be differential equations, and I'm the only one in the room. So let's get started from the graph. I would ask if there are any questions, but there's no one here to ask. Now, my computer yesterday and today has been doing some strange things. It seems to be stable now, but I have to sort of keep an eye on it because it's, like I said, doing some strange things. But anyway, here we are. Would ask, like I said, if you had any questions, but nobody's here to ask. So my mark here is that we're in section 1.2. Chapter 1 is Introduction to Differential Equations. Section 1.2 is Initial Value Problems. And we were just about to talk about existence and uniqueness. Okay? These are two fundamental questions that arise considering an initial value problem. Okay? First, does a solution of the problem exist? So there's the first question. And let me get my pen set up. There we go. First question, does a solution to the problem exist? Again, I abbreviate like crazy. Does a solution to the problem exist? And if a solution exists, is it unique? So, if yes, is it unique? Now, what that means is that the only solution, or are there other solutions that might be valid and may actually be the ones that work? Now, this is dealing with initial value problems. You may have thought, well, wait a minute, by establishing the initial value, don't you zoom in and find the unique solution? Well, guess what? Sometimes it may not exist, not in the domain that you are searching or something like that. Or if it does, there may actually be other solutions out there. Okay? Or at least that's what we have to consider. So for the first order initial value problem, like we set up last time, meaning first derivative is in the differential equation, that's the maximum derivative there, and you have one condition. Now, for existence, and that's what this one is, the questions are, does the differential equation dy dx, okay, first order, equal to some f of xy, in generic forms here, possess solutions? And notice we said solutions, okay? There's the first question. Does that possess a solution? Do any of the solution curves pass through our initial condition? There's our initial condition, x0, y0. Now, if the answers of those are true, or yes, then are these solutions unique? Okay? And what we ask there is, when can we be certain that there is precisely one solution curve passing through the point? When can we be certain there is precisely one solution curve that passes through. I'm abbreviating like crazy. Our initial value x0, y0. Okay? When can we be certain? Okay? Now, if you look back at examples 1 and 3, the way they're written, I think I even pointed this out to you on at least one of them, find a solution is used deliberately to suggest that there may be possibility of other solutions. At this point, it has not been demonstrated that there is a single solution for each problem. Here is an example, example 4. So this will maybe come close to answering at least some of these questions. Okay? Let me erase this and do example form. They claim here that y is equal to 0. I think we've hit this before. And y is equal to 1/16 x to the 4th. Seems like we've hit this one a couple of times. Satisfies the differential equation dy dx is equal to x y to the 1/2. Okay? And the initial condition, y of 0 is equal to 0. Okay? Now, y is equal to 0. Take a derivative of that and you get y prime is equal to 0. So then you would have 0 is equal to x times 0 to the square root of 0 is 0. So yeah, that works. And it fits the initial condition that when x is equal to 0, y is equal to 0. Because guess what? Y is equal to 0 everywhere. So x equals 0, y is equal to 0. So that certainly works. And I think we've tested the other one too. Derivative of y equal 1/16 x to the 4th. Derivative of that would be 1/4 x cubed. That would be the derivative. And 1/4 x cubed. Okay. That would be equal to x times the square root of x. Square root of x would be 1/4 x squared. And that certainly is 1/4 x cubed. And when x equals 0, y is equal to 0. So both of those solutions satisfy the initial condition. Okay. Now, at the initial condition, obviously, both of these solutions have a common point, and that's basically the only common point that those two have. But there we have it. So it does have two solutions. So it's number one exists. The solution exists, but it's not unique. Okay. In your text, if you have your text, a way to look at it, you'll see that, and I'll try to just do a rough sketch of this. I'm not going to do it to scale or anything. Y is equal to 0 would be, yuck. Okay, if I could draw a straight line, y is equal to 0 would be along that straight line. So let me erase this other stuff that is distracting here. And the second solution, y is equal to 1/16 x to the 4th, well, that would be a function that comes down, flattens out around 0, and then goes up pretty sharply. That's not very uniform, symmetric, but if you look in your book, you'll see it is. So both of those do satisfy the differential equation and meet the initial condition. Okay? Now, here's just a statement, and it's got so many weasel words in it, it's hard to imagine why they even bothered writing it, but it's okay. Within the safe confines of a formal course in differential equations, one can be fairly confident that most differential equations will have solutions, therefore they do exist, most will, okay, and that solutions of the initial value problems will probably be unique. Not definitely, but probably. Real life, however, is not so idyllic. Therefore, it is desirable to know in advance of trying to solve an initial value problem whether the solution exists, and when it does, whether it's the only solution of the problem. Since hey, we may have a student. Yes, we do. We've broken the ice. Okay?
Good morning.
Good morning. All right, good deal. Thank you. Paper in. Excellent.
I went about that one different. As far as I know, I did one on Isaac Newton already earlier.
Uh-huh.
I think it was Cal 2.
Uh-huh.
And I think Nimitz for Cal 3.
Right.
So they kind of tied in with the ODE. So
right.
I was like, well, I'll just try to do something as far as the benefits of differential equations.
Right.
So
okay.
I'm not used to it. So I know the format might be a little bit off, but as
right.
far as the arrangement of it, right. It's just the concepts are going to, hopefully they're going to fall on top of it. Not
okay.
that let you know about my grade.
All righty. All right. So Charles is here.
Yes, sir.
I had started the morning. I got up here a little early, got set up, and started the morning because I was here early trying to get names into the roll book because I had a new student show up in a class yesterday, okay? So I went down to the records office and said, are you still adding students? They said, probably not anymore. So I started doing that, and nobody was in here, so I was busily doing that, and then suddenly looked at my computer and thought, whoop, 8:33. So I got off to a little bit of a late start today myself, but so far, thank you for being here. You're the only one. But I don't have this class in the roll book yet. Today's 4 June.
Not the follow on Thursday.
Yeah.
It's going to be difficult to try to get on Thursday.
Okay. All righty.
Because of the project we got going on.
Right.
So Thursday.
Okay. Well, try to record everything.
Yes, sir. I'm probably recording when I missed last Thursday. So.
Okay. Now let me also say this. My computer has been doing some strange things lately. One thing is the power cord sometimes connects and sometimes doesn't. I wiggle and jiggle and stuff and usually can get it going. But when I'm here writing and doing things, it may actually work loose. And if it does, then the battery isn't very good, so it runs down the battery really quickly, and it may shut itself down. Now, I don't know if that's what happened yesterday, but something else strange happened yesterday, and it just got hung up. And this was in my second class yesterday, and I had to actually shut things down and bring them back up. I think it was when I was trying to log into my second class, I just couldn't get it to do anything. So I had to shut it down and bring it back up. And as a result of that, the first class didn't finish uploading. I didn't notice that until the end of the day. So I went back to put the first class in. I still had it, so I could. And then at the end of the day, I don't know why I did this, because I always do it the other way. Rather than just letting the computer go to sleep with that on there, I shut the computer down, and it lost it again, and I had to bring it back up last night and do it last night and let it run overnight. It finally loaded this morning. So there may be times when it will not work. That's what I'm getting at. Either my computer, my bad mistakes, or something external. Like I know one time the school forgot to pay Screencast-O-Matic and they shut us out. So there may be some times when it doesn't. But what I'll do is I will leave, the 10 o'clock scholar. Okay, good. Okay.
Sorry.
No, glad you're here. Okay. So sometimes, but what I do, I'll leave the old ones out there, and only when I record a new one do I take the old ones off. So the stuff you'll see at the top are old, things in at the bottom are the new ones. And if you happen to see a gap in the bottom, go and find what fills the gap up above. Okay. All right. So just have gotten 2 students in. So let's go back to, well, I've already started. We started on page 17, if you got a text. This is in section Chapter 1, Introduction to Differential Equations, 1.2, Initial Value Problems, and we started talking about existence and uniqueness, and we just basically finished example 4, which you see the remnants there on the board. So you can go back and listen to that. And I was reading through the next part, because I didn't know who had books and didn't, but I was just about at the point to write down Theorem 1.2.1. So since it's a fairly long theorem, I think I'll delete this. Is that okay? Okay. And then pick up, and this is right at the bottom of page 17 if you're trying to follow on an e-book or something. Okay. I don't know how e-books do page numbers, but hopefully you can follow that. So here's Theorem 1.2.1, existence of a unique solution. Let R be a rectangular region Now, I don't know how important it is to be a rectangular region, but that's usually what we'll let R be, is a rectangular region in the XY plane. Okay? And this is what makes it rectangular, bounded by, X is bounded between A and B, and Y is bounded between C and D. Okay? That contains some point and this is x0, y0. I can't write. I get to thinking ahead of where the pen is, and x sub 0, y sub 0. Okay. Now, the region contains that. You know, it's a little confusing, all the big word, all the lengthy words here, but there's some point x0, y0. The x0 is between A and B, the y0 between C and D. You know, that's in this region, this rectangular region, okay? In its interior. Now, what does that mean? X sub 0 is not A or B, has to be in between them, and y0 is not C or D, it has to be in between them. It's an interior point, not a boundary point, okay? That's what we mean by that, okay? Now, period. Okay. If f of xy, okay, now, usually what the f of xy is the function that your derivative is part of. Now, remember, all right, yeah. Trying to see if they're dealing with it. It appears they're dealing with only first order, but I don't think this is limited to first order. So if f of xy and the partial of f with respect to y. Now, at least one of you is in Cal 3 now, so you haven't hit partials there yet. Have you had Cal 3 yet?
Yes, sir.
Okay, I thought so. Okay. So, partial derivatives, are you familiar enough with them to know what I'm talking about with that symbology? Okay. So, the partial of f, since f is a function of two independent variables, x and y, you can't just take a derivative, you have to take the partial. Partial of f with respect to y. So if that partial, both the function and partial of f with respect to y are continuous on the region R, that rectangular region R, then, okay, there exists oops, I can't write. Some interval thought we already had the interval determined. Some interval I sub 0, and here's what that interval is. I'm going to write it on the line below. It's between x sub 0 minus h and x sub 0 plus h, okay? For h, some positive number. Could be an extremely small positive number, it doesn't matter. Contained in AB, now remember AB is a closed interval because of these equal signs there, okay? Okay. And a unique solution, that's what we're heading for here, a unique function, not solution but function, okay? We're going to call this y of x, defined on I sub 0, that is a solution of the initial value problem. Remember IVP, initial value problem. Now, they mentioned the initial value problem 2, and that's what I thought they were getting at earlier. If you go back at least one page, on page 15, you'll see that description. We are dealing with first order differential equations then, dy dx equal to f of xy. There's the f of xy. That's what the first derivative is equal to. And you have an initial condition y of x0 is equal to y0. Okay? So, there's our situation. We have some rectangular region between x and y, okay, on the xy plane. That's between a and b and c for x and c and d for y. Contains some point x0, y0, which happens to be our initial condition point, okay? Okay, in the interior, not on the boundary, but in the interior. Now, if the function f of xy, which is what the derivative represents, okay, and the partial of f with respect to y, okay, which would be very close to what your first derivative is here. This is dy dx, that's partial of f with respect to x, but you see dy dx is that derivative, is that function, so it's not really the same thing. That's the partial of that function with respect to x. If both of these are continuous, on R, within R, then there is some smaller interval, I sub 0, typically smaller, such that on x, you pick the x0 here, and then you do a plus h and a minus h. So some direction on either side of that, where h is positive, contained in that a to b, okay, there exists that interval contained in that, and a unique function y of x defined on that interval a to I sub 0 that is a solution to the initial value problem. A lot of blah blah blah, okay, and it's a pretty vague seeming deal here, okay. So that's theorem 1.2.1, okay. We'll call on it when we need it. I don't think that will be very often, but we'll just sort of assume that works, okay. So let's do example 5, which is revisiting example 4, which we just did, okay, which had two solutions, remember? Okay. So it said we saw in example 4 that a differential equation, dy dx, we've had this now several examples, dy dx is equal to xy to the 1/2, okay? rather strange differential equation. Okay? First order, ordinary, of course, not partial. Ordinary, first order, not linear, because the y is to the 1/2 power. So it's not a linear differential equation, and that doesn't matter. Okay? We saw that this differential equation possesses at least two solutions whose graph passed through 0, 0. We found two. So we say at least two solutions through 0, 0. Initial point 0, 0. Okay? Now, let's take a look at that. The function f of xy, that's what that derivative is equal to. That's x y to the 1/2. Okay? And the partial of f with respect to y, now, you remember how to do that? Or you may not have had it yet. How do you do the partial of f with respect to y? Anyone remember the rules? Not quite, okay? What you do, a partial with respect to y. So here's your function. We're taking the derivative, the partial derivative with respect to y. Now, we're not doing partial differential equation. That would be on the scope.
Wouldn't it be x divided by y to the 1/2?
Okay, you're awfully close. Okay? What you do is take the derivative of this with respect to y, treating the other variable, x, because you're not taking the derivative with respect to x, as if it's a constant. And that gives you something awfully close to what you just said. So this partial of f with respect to y would be 1/2 x y to the minus 1/2. So it's almost what you said. You left off the 2, so it'd be, writing the way you said, x over 2 times the square root of y, or y to the 1/2. Yeah. So there's the partial. Now, notice what the deal is here. Okay? They write it as y to the 1/2. Oops, hit the wrong thing. So let me write it that way too, just so you won't be confused. Okay? Okay. Minus 1/2, put it downstairs. Okay? Now remember what the deal was on it? These must both be continuous functions at that value. At that value, okay? This is continuous. That one's not. Because that has a y of 0 in the denominator. Can't do it. So you see, that's why this had two solutions at that value. But you see, it didn't meet the theorem, the uniqueness theorem, because it was required that these two functions, this be continuous, which it is, but that one is not at that point, because that's not even defined at that point. So you see, that rules out this differential equation from passing the theorem. So that's why it wound up with two solutions, because it didn't meet the conditions of the plane. It shows that they are continuous in the upper half plane defined by y greater than 0. The theorem enables us to conclude that through any point x0, y0, as long as y0 is greater than 0 in the upper half plane, there is some interval centered at x0 on which the given differential equation has a unique solution. Thus, for example, without even solving it, we know there exists some interval centered on 2, y2, I'm not sure, on which the initial value problem does exist. Yeah, okay. y2, you pick some point other than the point there, and yeah, now to pass through 2, it has to be the one solution, which was the 1/16 x to the x cubed, wasn't it? Whatever, no, x fourth. That was the solution the other one doesn't fit. Okay? So that one does have a unique solution. If you choose some interval and a point in that interval, then you're fine. Okay? Again, a lot of blah, blah, blah. Okay? Now, that took care of your existence of a unique solution. Okay? Now let's look at that interval, that I sub 0. Suppose that y of x represents the solution of the initial value problem 2, which is the one we've been talking about. The following three sets on the real axis may not be the same. The domain of the function y of x, the interval I over which the solution y of x is defined or exists, and the interval I0 of existence and uniqueness. Okay? Now, what follows is a bunch of blah, blah, blah. Okay? I'm not saying it's not important, blah, blah, blah. I'm just saying that most of the time, and again, being very, hedging my bets really big here, most of the time you'll be able to see whether, if you look at it carefully, wait, that's not going to work here, okay? But sometimes you forget to look at it carefully. But most of the time you will be able to detect that. So I'm not going to do anything more with that because it's mostly words. No way you can sink your teeth into it. They do say see problems 31 and through 34 in the exercises, and hopefully that will help you see what's going on here. All right, so that finishes the section. Again, the remarks are probably worth reading, but don't get bogged down in them. Let me just mention, and I've already mentioned these before, you can have situations which you have boundary conditions as opposed to initial conditions. Now, the boundary value problem, you know the value here and over here, okay? That's not going to give you necessarily a unique solution. Initial value problem, you know the function here and maybe the first derivative here, maybe the second derivative here, but you're always at that same point. As soon as you do a boundary value problem, now you have 2 points you're dealing with, and something may be going on here that's not going on there, and again, you could have 2 solutions that meet the same boundary value problem, boundary conditions. So there is a difference between boundary value problems and initial value problems. The boundary conditions BC and the boundary value problem BVD, okay, we're not going to do too much with them, but they put them in here just to remind you initial value problems are different from boundary. So, exercise set 1.2. Now the answers to selected odd number problems are back in the back. Okay, so try to do number 1. Do either 3 or 5 or both if they're back in the back, which I think they are. Either 7 or 9 or both if they're in the back. And either 11 or 13 or both, and I think they're both in the back. All right. Try to do 15 if it's back there, I believe it is, and any of the odds 17 through 23 if they are back there, and I think they are. Then try to do either 25 or 27 or both, okay, if those answers are in the back, which I think they are. And then, I'm not as certain about these, but try to do any of the odds 29, 31, or 33. I think those answers are in the back. Take a look first before you start into them so you can check and make sure you got the right answer. Then do either 35 or 37. I think both of those are in the back, and they give a whole lot of conditions here, so you just have to work through those. Now, both of those have graphs, and you can deal with that. And then any of the odds 39 to 43, if those answers are in the back, and I think they are. And those are the ones that we're talking about right at the end of the discussion. Now, the discussion problems, you can take a look at those, read through them, think through them, but most of the time these don't have answers in the back. Those that do, you may want to actually do, but most of the time they do not. So any questions on 1.2? All right. Now we get into, and I think this was one of the elements in your course description, but maybe not. I have so many different courses I'm teaching, I can't keep up with what the course descriptions are. But I believe there was a little bit mentioned on modeling. This is going to be close to most of what we do in modeling. So we're going to do this here in 1.3. All right. In this section, we introduce the notion of differential equations as a mathematical model and discuss some of the specific models in biology, chemistry, and physics. Okay? So, what is a mathematical model? The mathematical description of a system or phenomenon is called a mathematical model. Okay? It's constructed with certain goals in mind, and it usually starts, and they give two things. Identify the variables that are responsible for changing the system. We may choose not to incorporate all the variables into the model at first, and we are also sort of specifying the level of resolution that we expect to get. Next, we make a set of reasonable assumptions or hypotheses about the system we're trying to describe, and those assumptions will also include empirical laws that may be applicable. No, that's a lot of blah, blah, blah. I don't know if this is going to be a good example, but it's the one that pops into my brain first. And it is a very complex thing, but just to give you an idea what we're talking about. Both of you either are in physics or have taken physics, right? Is it still mechanics, or are you in electricity and magnetism yet?
Well, I don't want to take physics.
Huh?
I don't want to take that crap.
You don't have to take electricity and magnetism?
Well, I'm taking it now.
You're taking it now. Okay. If you ever had gotten to it or even get exposed to it, electricity was not understood very well at all. It started out being a parlor game with static electricity. You rub amber with wool and shock your friends, and people did, and that's about all they knew of electricity. Now, way back then, magnetism wasn't very well understood except for its practical applications. Rub a needle on a magnet and it becomes magnetized, and put it to float in something, and it always pointed pretty close to the north, okay? We understood that, but that's about all we understood. Those were miles apart. No one even made an assumption there was anything to do with shocking a friend with a piece of amber or following a ship's compass, okay? Why would anyone think there was anything to do with it? Okay, but the more we started learning about electricity, especially, it started advancing. And then they found currents, and they studied currents, and suddenly discovered that an electric current, a direct electric current, produces a magnetic field. Oh, wait a minute, there is a connection between these two. And sometime much later, they found out that by spinning or moving a magnet through a coil, you can produce electric current with no battery involved. Whoa, there is a connection between these two phenomena. Well, that's about it. It was a ooh-ah, wow, there's some connection here. And there was a Scottish physicist engineer named James, and it's pronounced Clerk Maxwell. It's spelled as if it's clerk. But, the Scots, they don't pronounce anything right. So he came up with, pretty much empirically, a couple, I think it was 4, really fairly complex partial differential equations that related electric fields and magnetic fields, okay? Really complicated, really amazing. And it made sense to him, okay? Everybody else said, oh wow, okay, just about like the other stuff. It was, I think, probably 2 or 3 generations later, we finally had the technology that we could test Maxwell's mathematical model of electricity and magnetism. Sure enough, I don't know if there's ever been a mathematical model that fit to a T better than that. We didn't even have the technology when he was doing it to test it. He came up with, just by his thinking, his observations and stuff like this seems to be the case. Those are called Maxwell's equations. Like I said, he probably started out with more than 4, maybe fewer, I don't know, but they've been modified and adjusted and combined and other things, so they're down to 4. Maxwell's 4 equations. Incredibly accurate model, mathematical model of what's going on in the real world of electricity and magnetism. And now we know that everything, or a lot of stuff, is electromagnetic radiation. Light, energy from the sun, I mean, all this is a whole spectrum of electromagnetic radiation described by Maxwell's equation. So that's the model. We're not getting into Maxwell's equation, but that's just to let you know mathematical models exist. Great mathematicians have come up with the concepts and made them work, okay? Now, kind of the reverse of that was what happened with development of calculus. Actually, it was probably very close to it. I always tend to forget his name. Laws of planetary motion. Goodness gracious. I always go blank on that guy's name. Very famous guy. I'll think of it at some point. He came up with a mathematical model explaining how the planets move. Copernicus, now, of course, much earlier. Say again?
Is it Kepler?
Kepler's law of planetary motion, okay? Copernicus had broken all the rules and said, look, it looks like the planets revolve around the sun rather than everything revolving around the earth. That would explain why the planets have such strange paths in the sky. Oh, almost heresy. If he hadn't lived somewhere up with what's currently Poland, he probably would have been. And it was published after his death. That was the other thing. He happened to be a monk, which is interesting because the church was very much against it, and that's probably why he waited until after his death and his assistant published his thing. Copernicus, this is. But before this, they had all kinds of mathematical models trying to explain the motion of the planets. Well, his came closer to any. It wasn't so mathematical, it's just the idea the sun's in the center and the planets go around it. Oh, that explains why they have such strange paths. And that we're spinning, and that's why the stars seem to, everything's making more sense now. Okay? But still didn't fit the paths exactly. Kepler then studied, incredibly mathematical minded here. He came up with the 3 laws of planetary motion. First is that the planets don't go in circular orbits around the sun. They go in slightly elliptical orbits around the sun. In fact, everything going around the sun goes in elliptical orbits. The planets are close to circular, but still slightly elliptical. The comets are incredibly elliptical. Pluto is pretty elliptical, so everything goes in elliptical orbits around the sun. Then the other 2 were the areas mapped out by the motion of the planet. So when the motion was close to the sun and moving rapidly, the area that was covered by that arc, that sector, is the same as when the planet's moving really slowly a long distance from the sun, and it's a very narrow, but it's a long. The areas are the same. Now, how he came up with this, I don't know. Incredible mathematical mind. But that was his model. And the third one is the relationship between the distance and the time, and one's to the second power, one's to the third power, and sure enough, that fits like a glove. And his model really fit nicely. He had no clue of why it worked. It was purely an empirical mathematical model. Okay? Now, Maxwell's laws, he had a lot better idea maybe of why it worked, but no one could prove it until generations later. I think Hertz was the one who did it. But Kepler had no idea. I believe he went to, I don't know if it was a friend, buddy, or just someone he respected a lot. Isaac Newton said, "Can you tell me why this works?" And Newton took it seriously and began delving into it. Could not describe it with math as we know it, or he was known then. So he developed a whole new mathematical language called calculus, okay, in order to describe Newton's plan. That was one of the things he did with it, giving justification for Newton's mathematical model. Kepler's mathematical model. So mathematical models are out there. They do exist. And you have to be careful with them, okay? I don't want to get into this too much, but it is sort of relevant. There are many kinds of mathematical models. Today, a lot of them are statistical models, okay? My wife's an epidemiologist. She works at UAB as a researcher, and they are constantly trying to come up with, or at least early in the years of her studies, they were doing things like trying to identify the risk factors for a certain disease, okay? And they would identify as many possible ones as possible, but they couldn't use them all. They did analysis of stuff, threw out the ones that didn't seem to have much influence, focused on the ones that had the most influence, and then hopefully narrowing them down in various things, they could get a certain degree of confidence, maybe probability of 0.1 or something like that, that maybe this would fit. If they really got a good model, 0.001 or something like that, that this would fit. So there's all sorts of models out there, but they all do these same things. You start with a bunch of variables, and all the ones you think could, you're probably going to miss some, but you start with some, and then you do analysis of them, figure out, hey, these don't seem to be very important. They do have some input, but not much. Let's focus on the strongest ones, okay? Makes it a lot easier for your study. And then, once you've done that, then make the assumptions or hypotheses. These are influencing this way, this is that way, and so on, and see what you get. Some models will fit pretty well, some will fit sort of well, some will fit very well, and some won't fit at all, okay? So that's what the purpose is, okay? Waste too much time on that. If you look at your text, if you got a text, I probably should do this, so let me go on and write this one in. It's the figure 1.3.1 at the bottom of page 22. Okay? It's a loop that doesn't have an end. It's a continuous loop. They put here, and I've been talking as if, and this is usually a decent starting point, assumptions and hypotheses. Okay, assumptions and hypotheses. Now, back when I was in the Navy, we used to have a not too nice description of what it means to assume. Oh, you've heard it too, huh? Have you? Okay. To assume makes the first three letters out of the fourth letter and the last two letters. Oh, okay. But in mathematical models, you have to make assumptions, okay? It's not quite as bad as the Navy. Were you in the Army or? Oh, okay, you just heard it somewhere. Okay. All right. You have to make some assumptions. You got to. You can't, as I've heard, this is fictional, of course, at the end of a big high-powered physics course, the prof handed out the final exam, and it only contained one question. The question was, find the universe and give 3 examples. Sort of, if you think about that, man, the universe is all there is. How in the world can you give 3 examples? But, different thing. You have to start with some assumptions, okay? And then the hypotheses are your guesses of what might make the system float, that work. And you'll test those hypotheses and stuff like this, throw them out. If they don't work, refine them. If they sort of work, keep going. So let's go on from there. And here is where, okay, I'll put this here. We'll express, this is where we come into play, express those assumptions, I'm going to abbreviate, in terms of, I'll write it out this time, but most of the time in terms of is ITO, in terms of DEs, differential equations. That's where we get into the picture, okay? Now, the block over here then gives you your mathematical formulation. Okay, you start with the assumptions, express them in terms of differential equations. That gives you your mathematical formulation. Then, here's the tough part, we try to solve those DEs, the differential equations. Some are solvable by techniques that we're going to be learning. Others you have to do numerically. But anyway, you go from that, and here when you do solve them, you obtain this, seems like this is sort of redundant things, obtain solutions. Okay, obtain solutions. Okay, now, here's the next step. Once you have what you think are solutions, now make predictions. Okay? Make predictions with the model. Okay? They put of the model. It seems like with the model would make more sense. Okay? So this is the next step. Okay? Now, what you do then is check the model. Okay? Predictions that you made with the actual facts. Okay? Now, this step, alter assumptions. If it doesn't quite match up or really does a lousy job, alter your assumptions. Or if it seemed to work okay but not super great, try to refine, increase resolution. Okay, of the model, and then go back and start over again. Okay, refine the assumptions, alter the assumptions, especially if this didn't work out too well. Okay, now like I say with Maxwell's equations, that mathematical model, an incredible mathematical model, really complicated, all like this, so many places it could have screwed up. I believe it was Heinrich Hertz, when finally they had the technology to test it, he did bingo! I mean, oh, you can't say that in Alabama. But it really fit like a glove. I mean, it did so well. There weren't many changes. There were probably a few little tweaks they did to it. But boy, those equations worked really well. Now, I'm not going to say that his was a mathematical, though it could have been. Einstein made a proposal back around the 1900s or so, early 1900s, that gravity was really a complicated thing. It was not just some sort of force at a distance, but it was actually some sort of a bending of space. I can't even begin to it. Space-time continuum, somehow he came up with this theory. Everybody went, ooh, okay, whatever he's saying here, I guess I can go along with it, or we'll try to believe it or something. But it was many years later that there actually was an event. It was some sort of an eclipse, and in that eclipse they were able to measure at the fringes of the eclipse that sure enough gravity seemed to bend the space-time continuum. Whatever that was, they were able to make measurements. Long after, I believe, Einstein had died, they were able to confirm his model work. So you see, we're always doing this, okay? You could even go further back and say Newton's 3 laws of motion. Actually, the first of those was done by Galileo. Newton refined it, took it around the circle a time or two, refined it, added 2 more to it, and those laws of motion worked, and people used them for centuries. But then Einstein came along and said, well, they don't quite work here and stuff like this, and he refined them and made some things, and did some pretty major changing of assumptions and stuff like this, and sure enough, his seemed to work in those really bizarre cases. So you see, all this stuff is constantly being done. And by the way, Einstein leaned on somebody to help him in his math. That somebody happened to be a woman, okay? Emmy Noether was her name. If my memory's right, she wasn't even allowed to go to college, but she was so bright. This one really high-powered mathematician recognized her brightness and let her sit in on those classes, even though she couldn't matriculate at the college. And so she certainly couldn't get a degree from the college, but she surpassed just about everybody there, and that's who Einstein turned to. When he needed help in math, he turned to Emmy Noether. Probably to others as well, but she was one. Yes?
They, back to gravity, they say, gravity, if you get, a trampoline or something.
As you get, yeah.
And then you put a ball in the center.
Right.
And how it, dips, I guess, and, everything gets attracted to it.
Right.
Is that the Bendy's kind of
That's been the example they use of Einstein's bending of the fabric of space. That's what creates the attraction. Yeah, that's what people use to describe whatever he was talking about, and that's a pretty good illustration of it. Of course, a model is a model. It isn't going to answer everything, and that's the very thing. Go back to the atomic model. When finally people realize there's more than 4 elements, earth, wind, this is Aristotle, earth, wind, fire, and water. Earth, wind, water, and fire, okay? 3 of those made a singing group in the 60s anyway. Okay, but that was beside the point. They found out, hey, these ain't all the elements. In fact, none of those are elements, they're nowhere close to elements. But when they started trying to manipulate these things, they were able to find out elements combined in what they call the law of definite proportions. So John Dalton came up with a model. He probably knew the model wasn't good, but at least it worked for then. This is sort of like the trampoline and the things doing that. He said, just imagine that every element has so many hooks on it, okay? Every atom has so many hooks on it. Carbon has 4 hooks, oxygen has 2 hooks, hydrogen has 1 hook. So H2O, the 2 hooks from oxygen 1, hydrogen here, 1 there, H2O. 4 hooks on carbon, 2 of them to go with the 2 hooks of this oxygen and that oxygen, CO2. So, yeah, it seemed to do. I think that probably John Dalton knew he didn't really have hooks, but he couldn't think of anything else, so that was his model. He knew it wasn't exact, but it had limitations. Now we know those are electron pairs that are binding things together, either electrostatically or covalently or, a variety of things like, your physics, your chemistry class, right? Yeah. Yeah. So, but his original model was hooks. just because he didn't know what else to call them, you know. It seemed like they had things like hooks that do it. We now know those are pairs of electrons that hook them together like that. Okay. So this is generally the idea. The key here is differential equations, and that's exactly what James Maxwell used. Only those are high-powered partial differential equations. Whoa, we're not going that far. All right, a mathematical model of a physical system will often involve the variable time, which is usually your t, and a solution of the model is then gives the state of the system, okay? And if you go and look at Maxwell's equations, there's usually four, you might say, degrees of freedom. Time is always one, and then the x, y, z's are usually the other. So you have partials with respect to all of those, okay? So we're not going to go into gory detail here, but just giving you several examples of models. Population dynamics, okay? One of the earliest attempts to model human population growth by means of mathematics was a English, can you guess this? Clergyman, okay? And economist, what a strange combination, Thomas Malthus, and you probably have seen his name before. So let me clear the screen. Okay. This is he lived in the late 1800s, 1766 to 1834. So now he was in England, and of course what we know of happening then when he was a 10-year-old was when we declared independence from England. Of course he had nothing to do with that. So, but just to get an idea, he was born just shortly before this country was born, okay, and lived until 1834, about the time when it looked like this country was about to fall apart, okay, so just to give an idea of the time frame there. But he came up with this model about 1798, and here's what he said, and this is sort of how it begins. The change, okay, I'm going to write it first and I'm going to say it. Now, that was kind of his starting off point. And let me encourage you to start thinking of derivatives and differential equations in terms of what they're saying. Now, he is the population, and he is saying when you have a dp, that's a change of population per change of time. So this is the rate of population change, dp dt. The amount the population changes over the interval of a given time period. Miles per hour in your car, the rate at which you're changing your distance with respect to time, that's called the speed. Well, this is the rate of population growth, the change of population with respect to time. That's what a different derivative is telling. He said this is proportional to the population itself. If you have a very small remote population, it's going to grow very slowly because you just don't have that many subjects in the population, so you don't have many matches to make, so it's going to be a very slow growth. But if you have a really large population, the rate of growth is going to be proportional to that. Now, he was doing this back at the time when empires were expanding and things like this, and this is what they were doing. You know, there were vast stretches of land, like in the U.S., native populations there, but they were few and scattered, okay? And, you know, he's saying that they're going to stay few and scattered until you get a good enough population basis there, then the population is really going to take off and grow. And indeed, we see that. So there's a differential equation. Now, but this is not an equation. This is a proportion. That is proportional to. The rate of growth of the population is proportional to the population itself. So how do we make that into an equation? You use a constant proportionality. You do the dp dt, the rate of population growth, is equal to some proportionality constant times the population itself. So Here's just a generalization. Anytime you see a proportionality, change it to equal K. Okay? Whatever follows that is equal K times that. So proportionality just shows the relationship. It's like if you're driving from here to Tuscaloosa, right? Since we're over on this side of town. Sorry, I didn't say Auburn, but that's super good. Right over here, just like, okay. Driving to Tuscaloosa. The time it takes you to get there is directly proportional to the speed you drive, right? No, I'm sorry. Okay. You're not driving Tuscaloosa. You're driving west on I-2059, okay? You're just driving west. The distance you travel is proportional to your speed. If you increase your speed, you're going to go further in a given time. If you decrease your speed, you're going to go not as far. It's direct proportionality. Well, what is the constant proportionality? That is your speed, okay? That's what determines it. So that would be I believe that, that would be it. Okay. So that's what we're talking about here. So you change the proportional to equal K, where K is your proportionality constant. Okay. Now, so that's one, population growth. Okay. Another, and you'll see these are awfully similar. Okay. Radioactive decay. Now, certainly this doesn't come into play until much later, and it actually came into play before we understood how it came into play, but now we know pretty much that the change in the amount of, this is the, it's just the amount of a given radioactive element. The change with respect to time is proportional to how much of that you had, okay, the amount you had. Or, to change it to an equation, dA dt is equal to K times A. Very, very similar type thing. Now, what do we mean there? And there's just all sorts of examples like this, but it's saying the rate of change, to give it a really gruesome example here, the rate of change of the number of atomic radioactive nuclei you have is proportional to the thing. Have you ever heard the term critical mass? Okay? That's what a nuclear reaction is doing. Yeah, those things are giving off neutrons and things like this. That's what radioactive decay is. It's changing.
Chem 2, I think we ran across that.
And what?
I think it was general chemistry 2. I think I ran across that.
Yeah, okay. And what happens with an atomic bomb, we go to an example, you get the critical masses, you force them together by an explosion of conventional weaponry, force them together, and then the rate at which those things interact goes up incredibly. That's what makes the explosion. So that's what happened. Now, hydrogen bomb, that's the fusion bomb as opposed to fission. You have several fission bombs you set off to force the hydrogen to fuse into helium, and when you do that, then the explosion is even more, way more than the three, I think it's usually 3 fission reactions that made that happen. So therefore, fusion is a tough thing to try to do. People are saying could be our future energy source. It's really tough to do because you need so much energy to get it going, and then it releases so much energy. So it's going on the sun all the time. But boy, you got the energy there. You have the critical mass. Okay, so that's beyond what we're doing here. But yeah, these are differential equations that describe or define what's going on in the real world.
There's this show on HBO. It's called like Chernobyl, and they say critical mass like all the time.
Oh, yes. Yeah, that was a very negative one, too. You see, okay, an explosion, nuclear explosion, that's very destructive. Now, what people tried to do, and I think that's why Einstein and many of the other physicists who were involved in this, they wanted to happen, not to blow up people, but to control this. And basically every nuclear power plant, including those making electricity here, or running ships. We have nuclear-powered aircraft carriers, cruisers, submarines, okay? Those are controlled nuclear reactions. They are very diligent and careful to control the number of, it basically is neutrons that are impacting other things, and they have the rods they put in to absorb neutrons or let them go, and that's what controls the reactions. And Chernobyl went out of control. 3 Mile Island went out of control. Fukushima went out of control because the tsunami hit and their controllers went down because the power went out, and stuff. And then you had a mess. I mean, a big mess. And Chernobyl is the worst of those messes. Actually, Fukushima could have been as bad, except the Japanese have built so many safeguards in, as you're supposed to. The Soviets, they were notorious for skipping as much as they could thought they could get away with. It bit them in the butt really badly in Chernobyl. Awfully in Chernobyl. We tried to put all those safeguards in, and we still had 3 Mile Island. Wasn't nearly as bad as Chernobyl or Fukushima, but still it happened.
Isn't 3 Mile Island still used today, though?
Still what?
Isn't 3 Mile Island still in use today? Like, it's not decommissioned, is it?
I don't know the answer to that. It may be. I would be surprised that it was, but it could be. Okay, but we came awfully close to having a very major nuclear disaster there. For a while, no, it wasn't. I know. Maybe it's back in. I don't know. But Chernobyl, there's still the, what do they call it? The elephant's foot. Is that what it's called? Yeah. No one can get anywhere close to it. There's no way to contain that radiation. No one can get close enough to try to contain the radiation. It's awful. Okay. Now, to put a human perspective on it, there was a group, I think based in Birmingham, we're really proud of them. I think it was mostly clergy, who, after that happened, way after it happened, people who lived not very close, but in the vicinity of Chernobyl, this is in what is currently Ukraine. At that time it was part of the Soviet Union. It is now in what is part is Ukraine. Decades after that event, some of their kids were born with birth defects, died. And a lot of the times, those families were very poor, they couldn't deal with it, they left the kids. So they were raised in orphanages. And a bunch of clergy from Birmingham area, and I'm sure from all the rest of the U.S. and probably other part of the world, started programs to try to help those kids. And I mean, even as simple as bringing them over just for a summer so they could develop in a fairly radiation-free environment. It helped their mental, physical, other cognitive development. They were able to develop more normally. Then they could move back to do, but they had a hard time developing in that environment. There was just enough radiation all over the place that was bad. Now, one of the clergy, here's the purpose of this story, actually adopted a boy out of one of those really awful orphanages. And he had been born with no right arm. I think he had a finger or two sticking out of his shoulder. hair lip, he had developmental problems, he had all sorts of things, underweight, lots of things. His parents had abandoned him, he was in the orphanage. They'd gone over so they went on and adopted him. And we happened to know people who knew them, and we were at an Indian Bible study of all things, and the pastors who were involved were at one of the churches that they knew this group, and I remember seeing the kid just months after he had come to the U.S., just a delightful looking little kid, really small, missing an arm, and just had operation on his hair lip, so he was sort of messed up there. But anyway, we knew of him, and knew through friends, the family, and stuff like this. Well, when he got college age, he was going to Jeff State and physical therapy technician, because he had learned to do all sorts of things with one arm, and had to learn that, and had been quite good at it. He golfed, he deep sea fished, he did all sorts of things with just one arm. And he still was a very small young man, but he was developing more normally, and a delightful person. But he wanted to be a physical therapy technician. Couldn't be a physical therapist. His cognitive stuff, he couldn't remember things well enough for that, but he wanted to help others who had physical problems. So he was trained to be that, but the math, he just struggled with math and went through Math 100 several times at Jeff State and could not get through. And I don't remember how it came about, but our Indian friend said, well, Charles teaches math at Boston State. We ought to send him there. And sure enough, the family did. And because I recorded the classes and stuff like this, the mother could listen to it and work with them on problems and stuff. And he sat right back there in that corner, and he took Math 100 here. And just was, now, the point, all that aside, and then he came back and did his Math 112 and sat right back there in the corner. Delightful kid, but he was second or third generation after that had happened. There was enough damage to his parents' reproductive organs and cycles and stuff that they produced a child with that. And this was generations after Chernobyl had happened. It was still having this effect. So this is serious stuff, we don't understand it completely, but it's pretty bad stuff. All right. And make a little statement here at the bottom of the page. A single differential equation can serve as a mathematical model for many different phenomena. As you see here, population, radioactive decay, all sorts of things. Now, I'm sure you've heard of carbon dating. Okay? That's when carbon atoms get online to see if they can make... No, that's not it. That's something else. Okay. That fits this too. That's radioactive decay. Okay? So, and that's how they estimate age of fossils and things like this. Okay? Not. Okay, what?
The carbon people meet.
Yes, that's how carbon people meet. Exactly. All right, enough of that. Okay, let's go on to some other examples of mathematical modeling. We're not getting into this deeply, but goodness, this thing just jumps like crazy. What is wrong with it? There we go. All right, Newton's law of cooling. Boy, Newton had his hand in everything. I mean, he developed a whole new mathematics. He came up with 3 laws of motion that revolutionized physics. He discovered things about light no one had ever even conceived. He used his calculus to come up with methods that we still use today to zero in on the zero of a function. And here he has his Newton's law of cooling and warming. Where did he even get into to have time to even think about thermodynamics? But here he did. Here's his differential equation, dt. Now, capital T is temperature, little t is time. So the time rate of change of temperature is proportional to, and here was Newton's insight, not just the time that was had, but the difference temperature, but the difference in temperature and the ambient. Okay? Oops, I'm sorry. I used O, the book used M. I'm sure there is a reason for M. What is the surrounding medium? Okay? I would never have used M. Okay, now what is that saying? Okay, now you take that, and of course, it becomes dT, that change of temperature per unit time is equal to some constant times the difference between the temperature and the ambient temperature. I want to use A because it's ambient, but that's what probably how I learned it, but they use the temperature of the medium. Okay? You probably use this all the time. If you pull something out of the freezer, the rate at which its temperature is changing is proportional to the difference in its temperature and the temperature of the surrounding air. That's how fast it thaws or cools. Okay, warms, I'm sorry. Or you pull something out of the oven, and the time rate of change of its change of temperature is proportional to its temperature coming out of the oven to whatever the room temperature is, the ambient. And it's that different. The closer they are together, the slower. The further they are apart, the more rapid the change. And that makes sense. No one had come up with it until Newton did. That's Newton's law of cooling or heating. Okay?
If you pulled something out of the freezer, and let's say it's at like 36 degrees, would 36 be the TM or the T?
No. TM would be room temperature. T would be the 36. But coming out of the refrigerator might be 36. Coming out of the freezer would probably be more like 26 or something 26. Like that.
Yeah. I was
But no, M is the ambient temperature, the room temperature, 70,
so
or whatever.
Number?
What's that?
It'd be a negative K?
Well, okay. The temperature, yeah, K would be negative. You're right on the money there. Because, you see, its temperature is below this temperature, so this is going to be a negative quantity, but the rate of change of that temperature is a positive. That temperature is going up in time. So yeah, that K would be negative. And coming out of the oven, same thing. Then this would be greater than that, but this is a decrease. Yeah. So yeah, K would be negative. You're absolutely right. Good observation there. Okay. Spread of a disease. Okay. dx dt is equal to kxy. Whoa, what in the world is a y coming up there for? Okay, now, this is a contagious disease, like a flu virus or something like that, spread throughout a community by people coming into contact with other people. Let X denote the number of people who have contracted the disease, and Y denote the number of people who have not yet been exposed. It seems reasonable to assume that dx dt, the rate at which the disease is spreading, is proportional to the number of encounters or interactions, but it has to be between people. If it was just between people who've already had the disease, no new cases are going to happen. So it's the interactions between people who have the disease and people who haven't had the disease. That's what it's proportional to. Okay? Now, where K is the usual constant of proportionality. So if it's a small community that is fixed population of N people, in other words, it's isolated group over here that don't interact with anybody else, then in that case, the Y and X are related. Because X is the number of people who've had the disease, and the Y who haven't, they're going to be some fixed number. Okay? So if the total number of population of N people, then this could be, and this is rather strange, but it is true, the Y is equal to number of population minus the X, people who have been exposed to it. You have this plus 1 in there. and it's rather strange. It sort of has to do with the individual. You have to have, it just has to be there. And so this, if you had a fixed population of n, then this would be kx times n, they put n plus 1 minus x. Okay. So then you only have one variable. Okay. And sort of the reason for it, the obvious initial condition for that one is that at time t equals 0, x equals 1. And that's probably where this comes from. So one person had to be exposed ahead of time, okay, to bring it in, to have the disease. Okay, now, my wife, being an epidemiologist and studying diseases, that's what epidemiologists do. She studies infectious diseases, so this is the kind of model. They use what is called a regression model to do that. And basically, this is sometimes called a regression curve. Okay? At first, very few people are exposed, there's very few interactions, but then when more people get exposed, the growth of the disease is just incredibly high. But then at some point, the whole population has been exposed, so it levels out. So this is your N up here. It can't get any more than N people, because that's your whole population. So this is usually your regression curve. In some diseases, that's a very steep, some it's very gradual. So that affects, how seriously, these things do, get transmitted. Measles is very steep. I hope y'all have had measles vaccinations. You don't know. You have. It's a good idea to have, because measles, even though, when I was growing up, way back in the dark ages, there weren't the vaccines, or they weren't sure about vaccines, and people thought better for kids to get it, they can recover from it more easily, and we can take care of them and stuff like this, than to do. But boy, it can be pretty aggressive. And so they came up with vaccines so people wouldn't have to go through that. But measles, I'm pretty sure of this, can affect the eyes really seriously. I remember my mom being a registered nurse. When we had red measles, we were in darkened rooms. We couldn't read, we couldn't watch TV, we couldn't do anything that strained our eyes, because it could, she overcompensated everywhere, but she probably did that there, but it is nothing to play with, And the older you get, the worse the consequences can be, because you don't recover as well. But also young kids could have other compromises, and it can be deadly, so it's a fairly serious thing right now. And yet there's huge portions of our population that are what they call anti-vaxxers against vaccines, because they're afraid, oh, this is some sort of government plot, No, it isn't. This is public health, And, my kids are healthy. They'll be okay. Well, okay, yeah, they may be, but, this other kid over here may have some immune condition that he can't be vaccinated. So your kid gets it, and you're going to be fine, but because this kid is immune compromised, when he gets it, it's going to wipe him out, maybe even kill him. So, no, vaccinate your kid so you can save this other kid over here, because he can't take the vaccination, okay? So she's epidemiologist, drives her nuts. Diseases can spread really fast, okay? The flu, if you did a curve, say, on infectious disease like the HIV, it was devastating to certain populations. It was just wreaking havoc because there was no known cure. Now they've got treatments, but so there's all sorts of things there. Pretty important application. Oh, and here's the one that Nolan's been waiting for. Chemical reactions. Okay? Okay? this is, I don't want to get too much into chemistry, but let me give you this. I love chemical reactions, okay? CH3, which is basically a, are you an organic or inorganic?
I don't know, Chem 2.
Huh?
I'm just in Chem 2.
Okay, what is it, 112? 113? Yeah, 112.
Yeah,
Okay.
right before you get to organic.
What's that?
It's right before you get to organic.
Yeah, right before you get to organic. Well, this is sort of an organic one. This is a methyl group, okay? And you have 3 of those attached to a carbon and then also a chlorine, okay? And this is going to act with sodium hydroxide, okay? And this is going to produce CH3, that's methyl group. Those 3 methyl groups are now going to combine with the carbon and the OH and have left over the NaCl. Okay. In other words, what's happened here is the hydroxyl from the sodium hydroxide is exchanged with the chlorine from, and I don't know these names very well. This is T-butyl chloride is what that is, and combining with sodium hydroxide to form T-butyl alcohol. That's what that is. Okay. That's organic. I don't know organic so well. But I do know that the hydroxide exchanges here, and so the hydroxide attached to the T-butyl part, and the chlorine combines with the sodium then because it's lost that, and that's NaCl. Saline, salt, okay, in solution, of course, okay. Now, what I wish this book did, in reality, most of these organic compounds go both ways, combinations. There's some equilibrium met there, and what they're saying here, only the concentration of the T-butyl chloride controls the rate of the reaction. But in the reaction, that's one. Okay, I'm sorry. There's a second reaction they have, and this is a completely different issue. CH3Cl, that's a methyl chloride, I don't know if they give the name of it, plus NaOH, and again it's probably a double reaction, but I'll do it like they do. You get CH3OH plus NaCl. Okay, in that reaction, 1 molecule of sodium hydroxide is consumed for every molecule of methyl chloride. That's what this is called, methyl chloride. This is T-butyl chloride is the top one. This is methyl chloride down here. And that forms methyl alcohol over here, CH3. In that case, the rate at which the reaction proceeds is proportional to the product of the remaining. So this is proportional to this alone. This is proportional to the product of the two. Okay, this is proportional only to this. This is proportional to the product of those two. So you would have 2 different reactions. In the first, this would be dx dt, where x is the molar concentration of your T-butyl chloride. Yeah, and that would be equal to Kx, proportionality constant times the concentration of T-butyl chloride. And this one down here, your dx dt, where x is that, is proportional to, or is equal to your K times alpha minus x times beta minus x. Okay, where the alpha goodness, they do a really lousy job of describing this. Two chemicals, alpha, A and B. So this would be the alpha, that would be the beta, okay? And that would be the rate of reaction. So two very close seeming equations here. One depends only on one, one's another. Different differential equation governing this one from what you have governing that one. It's a lot more complicated down here. And you just have to understand organic chemistry to know why that happens, but sometimes that's the case. And that's what chemists spend a lot of time doing, studying those unusual type situations. Okay? There are all kinds of problems like this, and this is probably taking way too long, but just to give you a flavor for how diverse differential equations can be doing, mixtures. Okay? I hate having to draw this, but since some of you don't have books. Here you have a spigot, and coming out of the spigot here is a solution. Okay? Here you have a container. Okay? And you also have a little mixer who is mixing, keeping all this mixed up well. And then you have a drain down here, and you have stuff coming out of the drain. So you have stuff coming into the mixture. Here's your level in here. You're keeping it well mixed, and stuff's coming out. Okay? So here we have coming in brine, which is salt water. Okay? And here we have a fixed amount here, 300 gallons. You're keeping that equal. So your input rate of brine is 3 gallons per minute. So that's going to be I'm going to call it B dt. 3 gallons per minute is going in. However, you have coming out, because this is a fixed here, your output rate is also, so let me put dBi for input brine, and dBo for output brine, dt, is also 3 gallons per minute. So B is measured in gallons, T is measured in time. So you see your units and your differentials, your derivatives, they all tie together. They go together. So what you're studying here is how much salt you have in that solution at any one time. Okay? And it all depends on what you have. So here's your equation, dA dt, which A is the amount of salt. How is that changing with time? It's equal to the input rate of salt. Okay? So that's dAn dt, and maybe I should have used A there, minus D, I'm probably not using it good, the output rate, DAO dt. So the stuff coming in is higher concentration than the stuff going out. So this is how much, the difference of what's in there. So this is rate in minus rate out. Okay? So, and then they go through and use some numbers in it. And it's sort of fun to do. I would say do it on your own. I don't think probably we need to take class time doing it. But you can work all this up with differential equations. Okay? Now, I haven't got my watch out. I'll get carried away with this. Y'all have to help me keep track of time, remember? How are we doing? 30 minutes left. Okay.
Oh, yeah, 35.
Yeah, that's what I was going to say. I think it's a little more than that. I hate to do it, but I need a bladder break. Okay, so let's pause here. We'll come back to all that I just said was not recorded. We picked up with the problem you have to read in the book. Sorry, that went by without doing so. The other 3 people who are not here, actually 4 people because one more showed up, but I don't know if he's coming back. Okay. I found out what the problem was. He had some incompletes from the spring, and I don't know if he's going to try to get those cleared and then come back, or just not going to come back. I don't know. Came late, yeah. I would let him in the course, but I mean, that's up to him. Okay. So this is the rate in the tank. That's what we got, 6 gallons per minute. Okay. Now, so the rate out of the tank, we got 3 gallons per minute going out, but the amount of salt that's in the tank, okay, the dAdt that's inside the tank here is A of T, that's the amount of salt in the tank, okay. The concentration of salt in the tank as well as in the outflow is A of T, that's the amount of salt in the tank at any time T, divided by 300, because you got 300 gallons. So that's your concentration. This is what I'm going to call I don't want to use I was using for input. That's the concentration. I'll put T, tank concentration at any time T, okay, is 300, and this is pounds, okay. The unit here would be pounds per gallon, okay, because you see you got per gallon down there. But you know the output rate is 3 gallons per minute. Okay, wait, okay. Let me work on this a little bit. This is C sub T, and this is in pounds per gallon. Well, you know that whatever your A of T is here, that's the amount in the tank, and you know you got 300 gallons in the tank. That's constant. So that's going to be the concentration in the tank at any time, okay? Now, multiply this by that, and the 3 will go into 300 100 times. The gallons go out, and now this gives you your A of T, dA of T, dt, is going to be the A of T divided by 100. That is the concentration at any time. That is your rate out. Okay? So, the net rate, and I'm running out of room to write because I've taken up so much room. As we said here, this is what we're looking for. The difference between these. This is your rate out. This is your rate in. So, to write that equation down, dA dt is equal to 6, this is pounds per minute, that's your input, minus, and what we just did, this is A of T, the amount in the tank, divided by 100, and this will be in pounds per minute as well, okay? But that's your differential equation, okay? Now, there's one other thing I'm missing here. Yeah, no, we got it. Okay. So let's rearrange this equation slightly. dA dt plus 1 over 100 times A is equal to 6. We just added that to this side. And this is what we later we're going to call the general form for a linear differential equation. The derivative, some function of the dependent variable, and and the output over here. So there is your differential equation. Okay? So we've done that. All right. Now, that was a mixture within a tank. What if you're talking about the draining of a tank? And how are we doing? We've got about 10 minutes, don't we? A little over 10 minutes.
13 minutes.
13 minutes. Okay. Okay, draining a tank. In hydrodynamics, any of you get into that? Okay. Which engineer? You're civil? No. Biosystems engineering? Oh, okay. Oh, earlier stuff was your kind of bag. Okay, I wish I'd have paid more attention. And you're mechanical. You may get into this kind of a thing. Hydrodynamics. I don't know, but it's a possibility. Torricelli's law. Hey, I can think of at least 2 or 3 paper topics there. Who was Torricelli? What was his law? How did he develop this law? Or how is this law used? Who uses it? You know, that kind of stuff. Okay? But in hydrodynamics, Torricelli's law states that the speed V, which I like to call d SDT or something like that, of efflux of water through a sharp-edged hole at the bottom of a tank filled to a depth of h is the same as the speed that a body, in this case a drop of water, would acquire in falling freely from a height of h, and that would be that the speed is the square root of 2gh. Okay? Now, you're in physics now, you said, right? Physics 1?
I took physics 1.
Huh?
I took physics 1 last summer.
Oh, you did physics 1 last summer. So you're not, you're doing chemistry now, that's right, okay. Yeah. Well, from physics 1 last summer, of course you remember this, okay? Don't you? Okay. You're already finished your physics, you're in physics 2 now. Okay, so you remember this from before. But you usually don't use this. It's usually physical science. They do something as simple as this. You can get that, the following object, this is from energy balance, okay? The energy at the top is all potential energy, mgh. The energy at the bottom is all kinetic energy, 1/2 mv squared, and those have to be the same. So if you had 1/2 mv squared is equal to mgh. Will y'all buy that without any arguments? Okay. If you solve for v, first thing you're going to do is multiply by 2. Okay. That will wipe out that. We'll divide out the m's, and they go away completely on both sides. Then take a square root, and you get v is equal to the square root of 2gh. So that's where that comes from. Okay, from your basically energy balance. The object is falling from the height of h and reaching the bottom, its velocity is that. And that's what the claim, Torricelli's law says water coming out of a tank is. That's the velocity at which it's going out of a tank. Okay. Suppose a tank filled with water is allowed to drain through a hole under the influence of gravity. We'd like to find the depth h of water remaining in the tank at any time t. So what we're looking for is h as a function of time t, where h is the depth at any time t, where this h is the original height that something is falling. But it's also at any time t, that's the height of the water is falling, so that is your variable. It's not just the original, that is your variable. Okay? Now, this v, little v, is velocity. Okay? Capital V is volume. Little v is velocity. Velocity. Capital V is volume. Okay? Your change of volume per unit time, dV, capital V, per time is equal to your area of the base. Now we're going to assume it's a circular base, circular tank, you know, a circular cylinder tank, okay? So that's going to be minus A sub H, that's the area, times the velocity at which it's going out, to GH. Now does that make sense? Velocity is distance per unit time, so this is volume per unit time. Area times distance, you know, is going to be volume. So yeah, this sort of makes sense. Only the thing is, the rate at which the volume is decreasing is a negative amount, because as the height goes down, the rate is decreasing. So that's why the minus sign is there. Okay? So there's your differential equation. Okay? Now, if you want to change that to, okay, that's your basic setup here, but you want to know how the height is changing. Okay? Well, what you have to do then is reformulate this dV dt, since that's a constant area, okay, then this is times dH dt. I mean, that makes sense, doesn't it? The volume is the area times the height. So the area is constant, so pull that out, and that gives you that. Well, now this you can solve. You're not really interested in that for dH dt, and notice the area is no longer important. It divides out, and what you have is dH dt is equal to minus the square root of 2GH. That seems like I've done. Okay, not quite. They introduce another H in here, and I don't know what they're talking about there. I see it in the picture. If the area of the hole is I messed this up. This is area of the hole. This is area of the tank. My eyes, I can't. With the cataract, I thought those were the same subscripts. They're not. Okay. So then they don't cancel out. Okay. So now we have the HDT. Let me get this cleaned up some here. Whoops. Sorry about that. Okay. Okay. Now, let me get that straightened out again. This is the area of the hole. This is the area of the tank. I think that's a 0 they use it. No, that's a W. I can't see. I don't know why they use W, but they use A sub W. That's the area of the tank. Okay, this is the area of the hole. So then, let me clean this up some. Minus area of the hole times the square root of 2GH. So divide both sides by area of the tank. So your dH dt, the rate at which the height of the water is decreasing, is minus. It's a negative because the rate is slowing. A sub h over A sub w times the square root of 2GH. Okay, got it right that time. Now, the sort of an interesting thing here, it says, notice that that is true even if A of t is not a constant. Here we just assumed it was a constant. If that's a variable, it's then just divided by A sub WT, how that's changing with time. Okay. Now, you said you weren't doing E&M? Electricity, magnetism, and physics?
Oh, I don't take physics
too. Okay, but you are taking it now.
Actually,
What's that?
we're covering it now, Dr. Brian.
Yeah.
We're covering it now.
Okay.
Now, I do know a little bit. You get
Kirchhoff's law. Yeah, Kirchhoff's law. Exactly. And this has to do with the second law. Did you read in the book? Is that where you got that?
No.
Oh, okay. It's right there. Yeah. I'll draw the circuit here. Now, how much time do we have? Whoops!
2 minutes.
I don't think we have time to do this. So, moving up a little bit here. Sorry, I probably did too much talking on Chernobyl and that kind of stuff. But anyway, we'll pick up next time and see. I shouldn't have taken this long in this section, but you get a flavor of how much you can do with differential equations. Okay? It's just all over the place. Everything using. Most of the time we pretend we just know the formulas. They really came from differential equations. Okay?
If you're doing Kirchhoff's law next, I notice it has 1 over C. Is that just like, I know there's 2 different capacitors, you have like a series and parallel, right?
Okay. There's 2 different circuits.
Yes, circuits.
Series circuits and parallel circuits. And then you have all sorts of combinations of them too.
Isn't 1 over C is for a...
What's that?
It has the 1 over C right here.
Okay, I don't know what you mean by 1 over 2. Let me look and
1 over
see.
C.
Oh, 1 over C. Okay. C is capacitance. And it's, it comes from, it's your basic formulas for voltages across capacitors, inductors, and resistors. Okay, one of them's a 1 over, one of them's as you see here, the L and R are multiplied, but it's 1 over the C, and it just comes from what's the relationship with the voltage. That's why one of them is 1 over C, with the others they're multiplied. Is that what you're asking? Or?
Well, I just remember I learned a little bit of it. I don't remember the Q's. The Q's just be like the
Q is charge.
The charge.
Yeah. So instead of using current, you use dq dt. So Q becomes a variable of interest. And again, remember at the very beginning, determine what variable you're dealing with. And since capacitor deals with the change of the charge, you can't really do the current. You need to do charge, but then you can express current in terms of charge as dq dt. So there are differential equations all over in that. And as you'll see, there's a variety of them, okay? And we'll get to that next time. So yeah, that's what we'll be talking about. Good deal. All right, let's see if there's any homework exercises. I can't imagine many here, but you might have some. You'll have to just look and see what's happening in the back of the book. Okay? If 1 and 3, either one of those is back there, try thinking through it, working those. That's on population dynamics. Newton's law of cooling and warming, that would be question 5 only. If that's in the back, then try to do that one. They have a graph here of it. Spread of disease or technology. I like the way they couple those together. Either disease or technology. You know what they're talking about there? Computer virus. The model is just like a disease. That's why they call it a computer virus. It spreads just like diseases. Product of the infected computer times the non-infected computer. It's just like a disease. And that's why they call it a computer virus. So you can do number 7 if that answer's in the back of the book. The mixtures, you can do 9 or 11, or both if you choose, if that's in the back. Draining a tank, Torricelli's law, that would be 13, and we'll pick up with the series circuits later. Okay? Good deal. Sorry if I ran over, and sorry if I took too much time doing sort of trivial stuff, but